Hello everyone and welcome to this section. In this section, we're going to provide an overview of support vector machines, okay, and how they work in general for classification, as a classification strategy. So let's get started. Let's assume that I have these kind of two classes, okay, which is, let's assume that they are, in our case, if there is a truck or there is a car or there is no car. These are kind of the two classes that we're looking for, okay? And here we have on the x-axis we have feature 1, and on the y-axis we have feature 2, okay? The question is, how can I separate these two classes, okay? First idea is, okay, we can draw this line, or maybe another one can say, okay, maybe we can draw this line, maybe we can draw this line, and so on and so forth. Which line is the best, okay? And that's where kind of the support vector machines work in a way. It tries to come up with the best line that actually classifies or separates these two classes, okay? All right. So what we could do, or support vector machine does, it actually looks at kind of the extreme points, which is here, these 2 points. And we call it kind of support vectors, which are the points that are extremely on the boundary, okay? I'm gonna show you a practical example of what do you mean by a boundary, all right? And then we choose these 2 points, and what we do is that we draw a line in between that tries to maximize what we call the maximum margin, okay? So it simply looks at these 2 points, these 2 lines, okay, which are these 2 lines passing through the support vectors, and it tried to kind of separate them as much as possible, create what we call the maximum margin, and draw that line in between, which is a separator, and that's what we call the maximum margin hyperplane, okay? It's very intuitive, makes complete sense. The question is, how can we detect these points? What do we mean by actually these points? All right, so let's take a look at what do you mean by this. Let's assume that I'm trying to classify, for example, cats and dog images, okay? All right, what do you mean by having 2 kind of support vectors? What do you mean by this? So let's assume that, again, I'm trying to classify cats and dogs. So these points indicates, like true cats. These are features of cats that are actually very pronounced. Like, everyone, even like, if you show it to like a 2 or 3 years old kid, can actually detect that this is an actual cat, okay? It's very clear, you can tell, okay, this is very, features of a cat, very clear. And that's why kind of, like these points are on the extreme values, The second point is, which is the other points, with the other extreme values here within the second class, which is, dogs, which is very clear. Anyone who will look at this, we're gonna detect, okay, that's an actual dog. Why? Because the features of a dog, it's very difficult to, for someone to look at this and say, okay, that's a cat. It's very difficult, okay? What about these points? These points are, again, are on the boundary, okay? These points are actually, some people might mess it up, might assume, okay, which is a little bit funny, you can assume that, okay, this might be a cat, might be a dog, I have no idea. It looks a little bit different. And that's kind of, these are the kind of the points which is, the support vector machine algorithm actually relies on. It relies on the gray values, which is not the pure black, not the pure white. It looks at the gray points and try to actually separate them first, okay? And that's why support vector machine is actually very unique classification algorithm compared to other classification algorithms, because it's kind of, like it looks at the extreme cases. Look at the kind of gray, like points and try to classify them. So the separator here, it actually works pretty well, all right? Again, I'm not gonna go into the mathematics of support vector machines. We're gonna see how can we use scikit-learn and use like, other just pretty much a couple of commands that can implement support vector machines for us, okay? All right. So the next point I wanted to discuss is there's some parameters that we need to understand pretty well when it comes to support vector machines, because we're gonna use it to actually get better results as we move forward. These 2 parameters are mainly what we call it the C parameter and the gamma parameter, okay? All right, so for the C parameter, it simply controls the trade-off between classifying training points correctly and having a smooth decision boundary. Okay, what do you mean by this? Okay, so I look at the C parameter as kind of, like a teacher, okay? This teacher or any teacher might be strict or might be very loose, okay? So for strict teachers, they actually apply very high penalty, right? So if any student does something wrong, the C parameter, if the C parameter is kind of large, if we have a large C parameter, that means we're gonna have a very high penalty. That means I'm gonna be very strict, all right? that means I will do my best not to make that mistake again, okay, in a nutshell. If my C parameter is very small, then that means I'm very loose, okay, which means the cost or the penalty of misclassification is low. What do you mean by this? Okay, let's take a look. So we actually have two kind of, ways. We can separate these two classes by kind of a straight line, as you guys can see here, or I can separate it in something like this, okay? And that's kind of the difference between having a small C value, having a small C values and a large C values. So if you have a small C value, you can actually generalize a little bit better. Why? Because the cost or the penalty of misclassification is low. If you do something wrong, I'm not gonna penalize it. I'm not gonna adjust the boundary line. I'm gonna be very, very strict. I'm just gonna make it, like general per se. That's when you have a very small C value. You can actually come up with a boundary that's, that's pretty smooth, pretty good, have a good generalization capability, which means if I get newer points, which is, haven't seen during training, I can place them somewhere here. It's gonna look pretty good. However, once I increase the C value, then I'm increasing, kind of making it more strict. That means the cost of misclassification will gonna be high, which means I'm gonna use a very hard margin. Then if the support vector classifier actually does something wrong, I'm just gonna penalize it if the C is high. That means I'm gonna bend that boundary much higher. I'm gonna bend it more, which means I'm gonna be very, very careful not to make any mistakes. Okay, what do you mean again? That means we're gonna kind of overfit the data. That means I can have a very specific boundary for our training data. All right, and that's why you guys can see here for C of 1, C of 10, C of 100, C of 1,000, the boundary becomes a little bit more stricter and a little bit more specific to our training data. Okay, the question is, what do we like? Do we like a very small C general, or do we like a very large C? Okay, so again, you have to come up with a sweet spot depending on your application. Obviously, I don't need the C to be very large, because once you do this, then you kind of, what we call it, overfitting. You overfitted the data. The model just doesn't understand anything but the training data. It can draw specific, clear, boundary between these two classes, and that's all what it knows. Once you come up with a new image, once you come up with a new point, it doesn't understand it. That's why you will see, the training accuracy is very high. The model will be amazing when it comes to training. However, when you present it to data that the model hasn't seen before, which is testing data, the model will fail miserably. Would be let's say 95%, and the other one gonna be, let's say, during testing, 75%. And that's where you guys can see the difference between the two. All right? And that's kind of the C optimization parameter. Okay, I'm gonna show you how can we use it when we run the support vector machine classifier. The next parameter that we want to use, we'll call it gamma parameter. And the gamma parameter controls how far the influence of a single training set reaches. Okay, what do you mean? So if we have a large gamma, that means we have a close reach, or closer data points have higher weights. That means if I have large gamma, that means these points very close to the hyperplane will have a very high weight, very large weight. Okay. However, if I have a small gamma, that means I have a very high reach. That means I have a little bit more generalized approach. Again, so if I have a large gamma, let's take a look. So if I have a large gamma, that means I'm going to focus mainly on these points, and I'm going to ignore these other points. These points are going to be ignored the far away. The closer points are going to be very mainly focused, which means I can pretty much, I might try to actually overfit the data. Okay, that's why you guys can see here, because I'm focusing on the data or the points very close only. However, for a small gamma, then I can have far reach. Then I can actually remove this and have wider reach, so I can have kind of a more generalized approach. Again, the gamma and C parameters, you guys can tune and change just to get, maybe better results. I'm going to show you as well how can we tune the parameters to get an optimized results. All right, and that's pretty much all what I have for this section. I hope you guys enjoyed it, and let's apply all our learnings to classify and detect objects within an image using hog features, support vector classifiers, and using as well some of the optimizations of the C and gamma parameters. I hope you guys enjoyed it, and see you in the next section.